Welcome back to College Algebra for Business. Today we're going to be talking about polynomial functions. We are also going to expand the scope of things that we're looking at to include polynomial equations. And we're going to do that because we want to pick up instances where you have a polynomial set equal to something, perhaps another polynomial, in an equation. And when you solve it for your variable, you actually get imaginary numbers. And you can do that. You can solve equations and get imaginary numbers. Those equations are just not considered functions. You do need to know how to deal with imaginary numbers in such situations. So this video is designed to refresh your memory about how you deal with imaginary numbers and complex numbers. Previously, we have said that a function such as this one, f of x equals the square root of x, cannot have negative numbers under the radical, so we have restricted the domain of x to x greater than or equal to 0. But for a while, we will be working with equations that can have imaginary solutions. For example, if y equals x squared minus 11x plus 38, we consider ourselves to have solved the equation when we find what makes that polynomial, what value of x, makes that polynomial equal to 0. Well, you can try a lot of guess and check with this polynomial, but there are not integer solutions to that. And as you'll see, there are not real solutions to that. So I think for this one, just for time's sake, I'm going to use the quadratic formula to solve it. So quick review, the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. If you thought I was going to sing that, I'm sorry to disappoint you. Actually, no, I'm not. Okay, x equals, what is b in this case? Well, we're going to put whatever b is in with that negative still in front of it. Well, in our case, b is negative 11. So negative 11 goes here, plus or minus the square root of b squared minus 4ac, and all over 2a. What are the values of b? Well, we already said that was negative 11. A, going back up into our equation, is, you don't see anything there, so it has to be a 1. And we have 38. Okay, we now have a positive 11 plus or minus square root of, oops, I forgot to put my 1 in the denominator there. All right, negative 11 squared is 121. And then we have minus 4 times a positive 1 times a positive 38. So we're going to get 152 over 2. So if we combine our terms under the radical, we will have 11 plus or minus the square root of negative 31 over 2. And there is our problem with this example and how it differs from what we've been doing before. We now have a negative under an even root. This time it's a square root. So before we go on, we have to talk about how to deal with a negative under an even root. So if a negative, let's take the simplest negative, negative 1. If it's not a real number, what is it? Well, we're going to define this as I. The square root of negative 1 equals I, an imaginary number. Actually, imaginary is not a very good description of what I is, because I does exist when you are trying to describe the behavior of electromagnetism. Imaginary numbers have very real effects in physics and in other fields. But let's get back to how we are going to deal with them. So since the square root of negative 1 equals I, if we were to square both sides of this, we would have, if you square a square root, the result is just the radicand, whatever was under the square root originally, and that's equal to I squared. So I squared equals -1, and the square root of -1 equals I. Now that we have defined those values, we can look at something like the square root of -4, which we previously said was undefined. Now we can define it. Now, if you have a value under the radicand, you can place the factors of that radicand under separate radicals, radical signs, still square roots, but this can become the square root of -1 times the square root of 4. And now we know that the square root of -1 is equal to I, and the square root of 4 is equal to 2, and those are multiplied. When we write this, we usually write the coefficient first, followed by the I, or the real number that is multiplied by I first. Let's check to see if this is true. We found 2I by taking the square root of -4. So if we square 2 times I, we should get -4. Well, let's see. According to the rules of exponents, this squared, because the 2 and the I are multiplied together, this is the same thing as 2 squared times I squared. We know that 2 times 2 is 4, and now we know that I squared is -1, so this is equal to -4. So it does check. That is how we're going to deal with imaginary numbers now. I do have one more thing to mention to you. Actually, imaginary numbers and real numbers are part of something called complex numbers. And a complex number is just a real number plus or minus an imaginary number. Okay, that's kind of simplified. Let's give some examples. 3 plus 2i is a complex number. Pi minus 1/2 I is also a complex number. Pi is irrational, but it is real. And in fact, a better way to write a general form for a complex number is to write it this way: a plus b, for which we understand that a is real and this part is imaginary. Now, I said real numbers were part of complex numbers. How is that possible? Well, let's see. 5 is a real number, but how can it be complex? There's no I there. Well, actually there is. There is a 0 times I, which gives you 0, and so all you have left is the real part. Now, can you have just an imaginary number to be a complex number? Sure. If the real part is equal to 0, then the imaginary part can be anything, like pi I. Or let's make that simpler and just call it a -3. And you can go ahead, because you have a plus and minus there, plus a negative number. Just write this as -3i. That is also a complex number. We generally refer to this as just an imaginary number, since the real part is equal to 0, and, who cares? So now that I hopefully have reminded you a little bit about imaginary numbers, let's go back to the problem, the equation we were solving. Now we can rewrite this, and by the way, all of this is x is equal to 11 plus or minus, we have a negative number under the radicals, so we can do negative I square root of 31 over 2. Now, the square root of 31 is irrational, so we're just going to leave it there because this is an exact answer. It is not an approximate answer. I don't want you to put square root of 31 into your calculator and round it off somewhere. Just leave it just like that. And so we have two answers for x. X is equal to 11 plus I square root of 31 over 2. Sorry, sometimes I put a little tail in front of my I, but it's the same thing. And 11 minus I square root of 31 over 2. And the order there doesn't matter if you're doing them from smallest, writing them from smallest to largest. Actually, this would be reversed, but I'm okay with either order. Now, the thing is, whenever we are working with equations and we find a solution, we should always check our solution by putting it back into the original equation. So all of this coming back up here. But that looks a little bit complicated, so let me remind you of a few things before we actually work with that. So let's look at what happens if you multiply first imaginary numbers, and then we'll expand that to complex numbers. So let's say negative 5i times positive 3i. So two imaginary numbers, one of them negative, one of them positive. Yes, you can have negative imaginary numbers. So let's multiply them. A negative times a positive will give you a negative, even if they are imaginary. 5 times 3 will give you 15. And then I times I, we treat it the same way we treat a variable, or any number really, is I squared. However, we remember that I squared equals negative 1. So what we really have here is negative 15 times negative 1, which gives you positive 15. So negative 5i times 3i is equal to 15. Let's do another one. Let's do negative 4i times negative 5i. So negative 4 times a negative 5 will give us a positive 20, and I times I is I squared. I squared is equal to negative 1, so this is 20 times negative 1, or negative 20. I have started lettering my examples because I'm putting a good bit on this page. So let's look at 3i times 2 minus 4i. Now I have a single term, 3i, multiplied by actually a binomial, 2 minus 4i. There are two parts to that, two very distinct parts. So instead of just multiplying all the numbers, I have to distribute the 3i to each of those values inside the parentheses. So 3i times 2 will give me 6i, and 3i times negative 4 will give me negative 12i squared. What I really have here, though, is 6i minus 12 times negative 1. Or that will give me a positive 12, which I'm going to write first, and then I have a positive 6i. All right, let's look at yet another example. And I guess I'll go back to white. Here we go. Let's look at what happens if you multiply two complex numbers that each have two terms in them. There's a negative 1 plus 3i and a 2 minus 5i. We have a binomial, in effect, times a binomial, because we're going to multiply the real times the real and the real times the imaginary, or first and outer to start with. So negative 2, negative 1 times negative 5i will give me positive 5i. 3i times 2 will give me a positive 6i, and 3i times negative 5i will give me a negative 15i squared, which is actually equal to 2. I can combine like terms, plus 11i minus 15 times negative 1, or negative 2 plus 11i plus 15, and I need some more room. I can still combine like terms, and I'm going to put the real portion of my imaginary number first. So 15 minus 2 is 13, and my answer is 13 plus 11i. That is what you get when you multiply negative 1 plus 3i times 2 minus 5i. Did you need that review to solve the equation for x? No, but you do need it to check your answer. Here is our original equation that we were solving, and here are our solutions. Now, actually, I just checked the online platform that we are using, and they prefer to write the second term in the complex numerator here as the square root of 31i over 2, and 11 minus the square root of 31i over 2. Now, to me, that's a bit of a problem, because if I extend this radical too far, like I just did, that looks like the I is underneath there, and it should not be. So what you may want to do to remind you where that bar stops is to just put a little vertical line there to say it's just the 31 that is under the radical, and that will avoid some problems. So we need to check this now. So for our check, we're going to go back to the original problem, and everywhere there's an x, we're going to put in 11 plus square root of 31i divided by 2. So for that x, that's squared, minus 11 times x plus 38, and if that equals 0, our check works. We did the right thing. So now we need 11 plus square root of 31i over 2. Wow. Just take a deep breath and do it one step at a time. So this squared means you can't just distribute that 2 to each term in the numerator because they are added together. We have to actually multiply 11 plus square root of 31i over 2 times 11 plus square root of 31i over 2. Okay, the denominator is easy, and we'll do the rest of it in a minute. So let me just copy it down so it's still there when I scroll down. Doesn't look like it's going to be equaling 0 yet, but it will. Just be patient. So in the denominator, I have 4 because we multiply straight across. 2 times 2 is 4. That's the easy part. But in the numerator, it's going to be a big numerator. We're going to do 11. We're going to distribute. 11 times 11 is 121. And 11 times the square root of 31i is 11 square root of 31i. And then we'll continue and multiply square root of 31i times 11. So we get another 11 square root of 31i, because this is forming a perfect square trinomial anyways. And then square root of 31i times the square root of 31i, I was getting ahead of myself, is square root of 31 times square root of 31 is 31, and I times I is I squared. And I'm going to go ahead and change this right now because I have 31 times I squared. That's 31 times negative 1, or negative 31 right there. And then I have negative 11 times and dot, 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 dot. Okay, I have to not forget the rest of that. But let's combine like terms in our numerator. What like terms do I have? I have 121, and I have a negative 31. So that's going to equal 90. Okay, and then plus 22 square root of 31i over 4. Now I'm going to go ahead and distribute up here my negative 11 into both terms. There, negative 11 times that entire fraction is going to give me negative 121 plus 11 times the square root of 31i divided by 2. And then I have plus 38 equals 0. So there I've written the whole equation, and I'm working out what it means to do the substitution that I did. Before I combine my fractions, I have to get a common denominator, and I'm looking at this and saying, boy, those are big numbers. I would like to reduce them if I can, so let's pull out a common factor from the numerator of the first term there. 2 goes into 90 45 times, and 2 goes into 22 square root of 31i, 11 square root of 31i times. And then in the denominator we have, of course, 2 times 2, so these will cancel. 2 and 2, they cancel. And my second term will not change a bit. There is no common factor that I can factor out. And the third term remains unchanged. So now let's combine like terms. In the numerator here, oh wait, look, I have a subtraction. So I have to subtract the entire numerator there. That means we have to distribute again. This negative has to be distributed to both terms inside the parentheses. All right, but we do have the same common denominator, so I can put everything over 2. I just have to be careful as I'm doing the rest of it. So I have 45 plus 11 square root of 31i. Subtracting the second term has no effect on the signs of the first. So a negative 121 minus 11 square root of 31i is what I get when I distribute that negative. Oh, and look at what conveniently happens. A positive 11 square root of 31i and a negative 11 square root of 31i add to be 0. And now I can move on and just write out 38 here. So what does my fraction look like now? It looks like, 45 minus 121. That gives me a negative 76, and that is divided by 2, and 38 is added to that, and yes, because that's equal to negative 38 plus 38, the left side equals 0, just as it was supposed to. So our check proves that our original answers were correct. Well, wait a minute. We proved this one was correct, right? This video is already long enough, so I'm going to leave it to you to prove that the value of x, that is 11 minus the square root of 31i, all divided by 2, is also a solution to this equation. The only thing that's going to change is a lot of the signs, but those are both solutions. It's a lot of work. Just take it step by step by step. So what if you weren't asked to solve an equation? What if you were only asked to check a solution? For example, you might be asked, is x equals negative 1 a solution to the equation negative 47x squared plus 5x equals 7x cubed plus 73? Not the simplest equation, but this is easier than what we just did. Because to determine if this is a solution to that equation, all we have to do is start substituting negative 1 everywhere we see an x. So in place of that x squared, it will be negative 1 squared plus 5 times negative 1 equals 7 times, we're going to cube negative 1, plus 73. All right, so this gives us negative 47 times 1 minus 5 equals negative 1 cubed is a negative 1 times 7 is negative 7 plus 73. Okay, so negative 47 minus 5 equals, let's see, 7 from 73 is what? 66? Yeah. Okay, so negative 47 minus 5 is negative 52. Does that equal 66? No. I would go through and double check my work here, but I'm pretty confident that I get negative 52 and positive 66, and so the answer to what was the question here is x minus 1 a solution to that expression? No. If it were, you would get a true statement. These two numbers would be equal if x minus 1 was a solution. Since they are not, it is not. You may ask, well, doesn't it have to be 0 equals 0? No, not for what we're working with right now. Because the reason we had to get all the way down to 0 equals 0 is that the original equation into which we were substituting our solutions here in the box was set equal to 0. So the left side did have to equal 0 because the right side did. In the problem we just worked with, the left side was some value and the right side was some value. And when we substituted negative 1 into each side, if it was a solution, whatever those values were, they would have been equal. They're not. It's not a solution. I feel like I'm repeating myself way too much, so I will see you in class. This video is simply a supplement to the material that is on Hawks, so make sure you read that material and watch the videos that they have provided.